Hi folks, happy storm day. In the interest of keeping pace with this course and not having a big crunch at the end, we're going to do a little bit of work on derivatives today. So on Friday we learned this important property. If we have x to the n, its derivative is going to be old power comes down front and the power goes down by 1. Okay. Something that came out of that was also that if we had g of x is x, then the derivative of x is just 1, or x to the 0. We also learned this constant multiple rule, or coefficient rule, that if g of x was 3x, the derivative would be 3 times the derivative of x, or 3 times 1, which would be 3. And lastly, we learned that if we had just a constant, so something like the number 2, the derivative of a constant term is 0. And that's different from a coefficient. Before we get too far into this, I just want to let you know in the video description you'll find links to practice questions on basic differentiation and product and quotient rules, which are the things we'll look at today. And there are also links to a 3.1 to 3.3 review and some solutions of that, and a video that kind of rounds up those topics. If any of those links don't work for you from the video description, just check the email that you got that has this video link in it. They're all in there. Okay, so we proved the power rule for positive integer exponents. So if we have x to the power of 3, we know it becomes 3x squared. But it does work for all powers except 0, and we'll have a more general proof later. Sometimes functions need to be rewritten in a convenient form in order to make use of this power feature, though. So if I have f of x is the square root of x, I really don't know how to differentiate that. But I do know that the square root of x can be written as x to the power of a half. And once I have it written in that form, I can use my regular differentiation rules. So seeing it as a fractional exponent, I can bring the old exponent down front, and the power goes down by 1. Now if my power was a half and I go down by 1, a half minus 1 is negative a half. I'm totally fine with you leaving the answer in this form. If you feel like you'd like to put it back into radical form, this means a half times, let's see, negative power means it's on the bottom, so this would be 1 over root x. Or the derivative of the square root of x is 1 over 2 root x. Okay. But again, we're happy to just leave it at this stage. So again, in the next one, we've got 5 over x cubed. You might be tempted to just differentiate the bottom, but that actually gets us into trouble. What we should do is write it in a form that's familiar to us, so that it looks like 5 times x to the power of something. So an x cubed on the bottom just means an x to the negative 3. Okay. And notice here, I've written it as f of x equals. That's because I haven't differentiated. I've just written the original function, or the original statement, in a different form. Now I'm ready to differentiate. So I use my rules. 5 is a coefficient, or a constant multiple, so it stays. The x to the minus 3 becomes negative 3 x to the minus, oh, careful here. If my power is negative 3, and I go down by 1, my new power will be x to the minus 4. Okay. So I'd have negative 15 x to the minus 4. Or if you're feeling fancy, you can write it as negative 15 over x to the 4. It really makes no difference. The last one's a little sneakier. We have 3x all squared. You might be tempted to just bring that 2 down front and say it's going to be 2 times 3. But think about this. This one's a parabola to start with. That means that its derivative should be a linear. So our general approach is put it into a form that we know what to do with. I've got that squared there. Let me just evaluate that. That'll be 9x squared once I get rid of my brackets. And so when I differentiate, I'm going to have 9 times 2x, or 18x. I did it safely, and I got the right answer. And it is totally fine if you skip right to the 18x. That's great. As we move forward, we'll see more and more of that. taking a look at a similar problem that's just a little more involved. We've got g of x is 3x squared minus root x, and we want the slope at x equals 4. In other words, we want g prime of 4. G prime means slope. So I'm going to want to differentiate this, and I look at it immediately, and it looks kind of rough because it's got that square root. So let me just put it in exponential form, because I know how to differentiate exponents. So again, I've written just g equals because I haven't differentiated yet. Now I will start to differentiate. 3 times x squared becomes 2x to the 1 minus 1/2 x to the negative 1/2. Or g prime of x is 6x minus 1/2 x to the negative 1/2. You can rewrite this in radical form, but we can also just use it from this form. We can just sub x equals 4 into this. Okay. So that'll give us, I need a little more space here. That'll give us g prime of 4, okay, which reads the slope at x equals 4, or the instantaneous slope at x equals 4, equals 6 times 4 minus 1/2 times 4 to the negative 1/2. Now, it is true that you have access to your calculator, but I really hope that everybody can evaluate 4 to the negative 1/2. That means to square root 4 gives you 2, and also to flip it upside down. So it would give us 1/2. So we get 24 minus 1/4, or 23 3/4. And you could write that a bunch of different ways. 23.75, or let me think about this for a second, or 95 over 4, all mean the same thing. So that gets us ready to do a little bit of practice. You could pause here and take a look at that basic differentiation sheet. There's no point in printing it out. I'll give you a hard copy tomorrow. But maybe do a few from 1, 2, 3, and 4. And I would just spend 10 or 12 minutes doing a few of those and getting an idea of what some of the basic differentiation looks like. Okay, so you could pause here and do a bit of that. And we're back for the second half. So the next thing we're going to look at is what happens if you have two functions that are multiplied together. So imagine that I have f of x is 2x minus 3 times, I don't know, 3x plus 1. Okay. And we're wondering, would the derivative of that be just the derivative of the first times the derivative of the second? Would it just be 6? Well, we can find out by multiplying through, and we'd get, let's see, 6x squared for f of x, just by foiling out, plus 2x minus 9x, so that's minus 7x, minus 3. I can clearly see that the derivative's not going to be a constant. It's going to be 12x minus 7. Something else must be going on here. And I'll give you the proof for the product rule at the end of this video, because we said that we weren't going to take anyone's word for how this stuff works. We're going to make sure that we had rigorous proofs for everything. But you might just want the property to begin with. So here's what it is. If you have two functions of x multiplied together, which is what we've got here. So it's almost as if our first part, which we're going to call u, is 2x minus 3. Okay. And our second part, which we're going to call v, is this 3x plus 1. The derivative, so let me just think of the original. I'm going to get rid of those x's. Let's just assume that u and v are functions of x. The derivative is the derivative of the first part times the second. That's u prime v plus the first times the derivative of the second, or uv prime. Now, some people write these in different orders. It makes no difference. So let's see if this actually works out for the f of x that we chose down here. So I said the first thing that we're multiplying together is 2x minus 3. If I were to write its derivative, that is 2. the derivative of 2x minus 3. v, our second part, is 3x plus 1. v prime is 3. Let's try and put this rule that we just developed to work. So it would be u prime is 2 times v, which is 3x plus 1. I laid them all out nicely to begin with in this kind of table here. Plus u, okay, which is 2x minus 3, by v prime, which is 3. Now, let's just work this out a little bit further. F prime is 6x plus 2 plus 6x minus 9. In the end, we get the same derivative that we're going to get by foiling first. Now, you might legitimately say, why the heck would we use this complicated process if we could just FOIL to begin with, or use the distributive property? And I think that is a fair criticism. Right now, all we've got to play with is polynomials, so you might as well FOIL first. But when we come into a function that's something like this, f of x is x squared times sine x. Well, there's not really any foiling out or distributive property we can exploit there. So we are going to need the product rule. For now, it doesn't matter whether you use it or not on this one in green, but there are going to be lots of situations where you do need it. All right, so that leads us, if we know how to deal with products, which means multiply, what happens if we have a quotient? So I'm just going to think of this as u over v. One thing that involves x over another thing that involves x. So why don't I set up one of these quotients? I'll do it in a different color. So we have something like this. 2x minus 3 over 3x plus 1. Okay. So notice here that it's division where both the top and the bottom involve x. If they don't both involve x, there are probably some other things we might be able to do to work around using quotient rule. Here's what the derivative looks like. If f of x is u over v, then f prime is going to be u prime v minus u v prime all over v squared. And again, I'll put the proof to this at the end of the video. Hopefully you'll be interested, but if you're not, no hard feelings. So when we say that, here's what we mean. The thing on the top, that 2x minus 3, is what we're calling our u, the numerator in the function. The thing on the bottom, that's what we're going to call v. So 3x plus 1. Each of those have a derivative, so u prime would be 2, and v prime would be 3. If I want the derivative of f, I just need to plug into this little quotient formula here. So let me pull it down so I can see it. Okay. So I'll have u prime, which is 2, times v, which is 3x plus 1, minus u, which is 2x minus 3, times v prime, which is 3, all over v squared. And there is pretty much never any point in expanding that bottom. Let's see what happens. If we work this out, we're going to have 6x plus 2 minus, and careful here, minus 6x, and this will be a plus 9, all over 3x plus 1 all squared. Okay. Or in other words, f prime is going to be 11 over 3x plus 1 all squared, which is kind of neat. It tells us that this is always going to have a positive slope wherever it's defined. Anyways, we basically plug and chug into this quotient formula. So let's try it in a couple. Okay. Oh, wow, that's a lot of problems. There we go. A little more manageable. So in A here, I have y equals x cubed minus x. Smartboard's not happy. X cubed minus x by 2x squared plus 3. Okay. So I have two options. I'm going to use this product rule business so I can get the practice. So the product rule says it's u prime v plus uv prime, where u is the first part of the multiplication, so it'll be x cubed minus x, and v is the second part of the multiplication. So that's going to be 2 times 2x, or just 4x. Sorry, I'm jumping to the derivative. V is 2x squared plus 3, and v prime, rather, is 4x. Okay, over here, u prime is going to be 3x squared minus 1. Okay, now I can plug and chug in that formula. The derivative, dy by dx, will be u prime, which is 3x squared minus 1, times v, which is 2x squared plus 3, plus u, which is x cubed minus x, times v prime, which is 4x. I can multiply all this stuff out. So that will give me 6x to the 4 plus 9x squared minus 2x squared. So that's plus 7x squared minus 3. And then I'll have plus 4x to the 4 minus 4x squared. And my smartboard's being a bit weird here. Put them all together, and we get 10x to the 4 plus 3x squared minus 3. There's our derivative. If we were to do it the other way, by foiling first, hopefully we get the same result. So there's the original problem written out again. Let's see, if I FOIL first, I would get 2x to the 5 plus 3x cubed minus 2x cubed, so that's plus x cubed minus 3x. And then once I differentiate that, I'm going to get 2 times 5x to the 4 plus 3x squared minus 3 times 1, or the same result. Okay. And I think it's pretty clear that it is slicker to multiply out first. So for now, probably do that on most of these questions. But once they start to get more complicated, you're going to need this product rule. Okay, let's try another one. So here we've got one that's 3x over x minus 1. This is division, so this will require the quotient rule. So u prime v minus u v prime all over v squared, where u is whatever's on top, okay, and it follows that its derivative is just 3. And v here is whatever's on bottom, and it follows that its derivative is just 1. Here, there's no FOIL workaround. We actually have to plug and chug with these values. But I'll just go u prime, which is 3, times v, which is x minus 1, minus u, which is 3x, times v prime, which is 1. And this is all over x minus 1 all squared. Don't forget that bottom squared part. Okay, what are we going to get? 3x minus 3 minus 3x. Again, we have a case where all the x's are gone on top. That's not always going to happen, though. The top is whatever it is. And I end up with that as a derivative function, which tells me the slope on the original anywhere. Let's do one more basic one that's either a product or a quotient. So this one is a little bit sneaky. We have 2x plus 1 times x squared minus 5x plus 1 all to the negative 1. When we have something to the power of negative 1, that means it goes on the bottom. In other words, this function is secretly a quotient, not a product. Now, there are ways that we can deal with it as a product, but not with the rules that we have so far. And even once we do have those different ways, it's still going to be easier to deal with this as a quotient. So let me write the quotient rule out. It's u prime v minus u v prime all over v squared, where u is the top, 2x plus 1, and its derivative is 2. Okay. V is the bottom, which is x squared minus 5x plus 1. And that means v prime is 2x minus 5. I always like to write out all those facts so that now I can just plug it into the quotient rule. So it's u prime v minus u by v prime. And you might say, hold on, why are we doing another one that's the exact same? There's one common error here that I want to just kind of point out. So I put the v squared on the bottom. I'm going to multiply out. The first part looks okay, 2x squared minus 10x plus 2. The next part, I'm going to FOIL this out, but I still need to subtract it all. So that's why I'm going to keep it in brackets. I'll have 4x squared minus 10x plus 2x, so that's minus 8x minus 5. And this is all over x squared minus 5x plus 1. And now I'll subtract. And I'm doing this piece by piece in the hopes that I don't make any silly mistakes with my signs. So it's minus 4x squared. We probably all would have got that one. It's the plus 8x that often goes a little off the rails. And then the plus 5. X squared minus 5x plus 1 all squared. Okay, let's see what we get. We'd have negative 2x squared minus 2x plus 7. All over x squared minus 5x plus 1 all squared. Now, if the top of that factored, we would probably factor it and look for opportunities to reduce. The top doesn't factor, so that's where we're going to leave it. So our quotient rule gave us the correct derivative. Just as a quick aside, one way that you can check whether your derivative is correct or not would be to go to Desmos. You can graph the original. There it is, f of x. If I graph my answer for the derivative, it looks like this blue one. And I can also ask it just to graph f prime, the derivative of f. And you can see that the blue one and the green one are the exact same. So I must have the correct derivative. One more question involving product or quotient rule. Here we go. Find the equation of the tangent to this function at x equals negative 1. Okay, so anytime we want the equation of the tangent, we need two things. We need a point and we need the slope. Here it's telling us that the point is where x is negative 1. I need to find the y value. And to find the y value, I just sub into the original. It literally says y equals. So let's see, what will it give me? Negative 4 on top and 1 on the bottom. Great. So the point is negative 1, negative 4. What I need is the slope. And to find the slope, we differentiate. So looking at this, I know that my u is 3x minus 1. That u prime is going to be 3. I know I need quotient rule because I have division involving x here. Okay, my v is 2x plus 3. And my v prime is going to be 2. So the slope comes from the derivative, which you can write as y prime or dy by dx. And let me just write it out here again. U prime v minus uv prime all over v squared. Okay. So u prime is 3. V is 2x plus 3 minus u, which is 3x minus 1, and v prime, which is 2, all over v squared. So that's 2x plus 3 all squared. Now, I could just sub in at this point. It's a bit of a mess, so why don't I try and clean up my derivative function first? But remember that the whole way through, this is just reading slope equals. So 6x plus 9 minus, let's see, this is going to be 6x minus 2. Notice I did that multiplication. I'm going to wait to actually subtract them so that I don't mess up my signs. I see on top 6x minus 6x, the x's are going to be gone. And really what's going on is I have a 9 plus 2. So I have 11 on top. I'm interested in the slope at x equals negative 1. So I'm going to sub it in to my derivative function. So that'll be 2 times negative 1 plus 3 all squared. Okay. Working that through, let's see. I'll have 11 over 2 times negative 1 is negative 2 plus 3 is 1. 11 over 1 squared. Okay, that worked out pretty nicely. Or dy by dx is 11. That is the slope of the tangent. Now that I want my equation of the tangent, I'll use my point slope formula. Y minus y1 m x minus x1. So just to recap, we already knew that our point was negative 1, negative 4. Negative 4. And now I know that my slope is 11. Okay, that's x1, y1, and slope. And we'll just sub into the point slope formula. So I'll have y minus negative 4. If you want to write it as y plus 4, I think so much the better. Slope is 11. X minus negative 1. Again, probably easier to write this as x plus 4, or y plus 4 rather. This is x plus 1. So y plus 4, 11x plus 11, or 11x plus 7. And I might just take a look at them on Desmos and see if I really do appear to have the correct tangent. Here's the graph of 3x minus 1 over 2x plus 3. Let me put in that tangent. Does it appear to meet at x equals negative 1? Yeah. Does it look tangential there? Yeah, it does. So seeing is believing. Looks pretty good. That brings us to the end of the material for this lesson. In terms of practice, here's what I think you should take a look at. On the product rule sheet, 1 ACE, 2 ACG, well, you can just read. Quotient rule sheet, do a few of the quotient rules as well. Really, spend 20 minutes doing a few products and a few quotients, and then call it at that. I had stuff from the book, but let's not do that. So what's here in ink for even answers, you don't need to worry about. All the answers for the sheets are on the sheets. Okay. So that brings us to the end of the lesson. For those of you who are interested in the proof of the product and quotient rule, here we go. These are a bit cumbersome, so hopefully the smart board will cooperate with me. So if I have f of x is u of x times v of x, f of x plus h is just same thing with x plus h's. Okay. It follows that the derivative from first principles is going to be the lim as h goes to 0. H goes to 0 of u of x plus h, v of x plus h. I'm actually going to leave a little space here. and put at the end minus my u of x, v of x. That's what we would get from first principles. Okay? And it doesn't look very helpful at all, and it's not very helpful at all. But there's a cute little trick that we can exploit. One thing that I can do here, and this is kind of the creative part of mathematics, is I can subtract u of x by v of x plus h as long as I add it as well. Now that initially does not look like it does too much good. But let's see what happens if I split this apart. So I'm going to keep on with this idea. I'm actually going to take my first couple of terms and make them their own limit. So u of x plus h, v of x plus h, minus u of x, v of x plus h, all over h. That's just the first half here. Okay. Plus the limit of the other stuff, which would be u of x, v of x plus h, minus u of x, v of x. And this is also all over h. Okay. And the techniques we need from here are actually not that complicated. So the stroke of genius is to subtract and add that u of x times v of x plus h. Now I can just do a little bit of common factoring. So you can see in the first couple of terms, v of x plus h is a common factor. I'll try and make that v as pointy as possible. v of x plus h is a common factor, leaving u of x plus h minus u of x. And this is all over h. In the other one, what's the common factor? Well, it's u of x. And it leaves me with v of x plus h minus v of x. And this is all over h. Now, some of our other limit rules say that we can split even further. And I'm not sure at what point this becomes more or less helpful. But let me just take that lim of v of x plus h out front as its own limit. Multiplied by the lim as h goes to 0 of u of x plus h minus u of x all over h. In the other piece, I have lim as h goes to 0 of u of x, could be taken out front, and then times the limit of the leftovers. And maybe you see it, maybe you don't. But as h goes to 0, v of x plus h, this part right here, goes to v of x. This part right here, on the other hand, is the definition of u prime. Over here, as h goes to 0, u of x stays u of x. It doesn't even care about h. And this bit over here is the definition of v prime. And just put in alphabetical order, that gives us u prime of x, v of x, plus u of x, v prime of x. Or, as we had said before, u prime v plus u v prime. So that's why the product rule works. It comes from first principles and just evaluating limits. We have something similar for quotient rule. So f of x plus h would be u of x plus h over v of x plus h. So if I wanted the derivative of a quotient, I go u of x plus h over v of x plus h minus u of x over v of x all over h. Okay. This is coming straight from the definition of a derivative. Just to be clear, in case you don't have it in front of you, that's lim as h goes to 0 of f of x plus h minus f of x all over h. So we're just using that. Now, when you look at this, you see it as a set of nested fractions. So we can use our usual gag for nested fractions and say, let's times by v of x plus h and v of x, both on top and bottom of the big fraction. And when we do that, our fractions will no longer be nested, which is kind of nice. And what we'll get is u of x plus h times v of x and I'm also going to end up with minus u of x by v of x plus h. Now I've left some space here. You can probably guess what's going to happen. But notice that on the bottom, we still have h by, don't really need a bracket here, by v of x plus h by v of x. And we need something neat to happen here. So we're going to subtract off and add on the following. Minus u of x by v of x. And if I subtract it off somewhere, I need to add it on somewhere. And where I put it, I'm just putting it in these places for convenience. But if you put them in a different order, eventually you could rearrange it, and no big deal. Okay, one thing we might want to do before we move too much forward is just deal with that bottom. So we can rethink of this as lim of 1 over v of x plus h. I'm just going to factor out the bottom of the fraction. V of x plus h by v of x. And then I'd have the limit of everything else. So it would be u of x plus h by v of x minus u of x, v of x. I'm going to write this in a kind of a funny way over here. Minus, I'm going to take out a factor of negative whatever. Now, the reason that I'm doing that is so that my second limit just has the problem of h going to 0. And the first limit here, as h goes to 0, all I'll get is v of x plus 0, which is just v of x, times v of x. In other words, I'll get 1 over v of x all squared. And that will follow me through all the rest of the way. Now, let's see what happens over here. I'm going to have lim of u of x plus h, v of x, minus u of x, v of x, all over h, minus, and this is all going to be multiplied together, so that was squared. Smart board. Minus, over here, I could split this into a second little limit. U of x, v of x plus h, u of x, and v of x. And we do that so that it looks kind of like it did for the product rule. Okay, so let me follow this through. I'll admit this is looking kind of abstract here. This is not the only way that you could think of splitting these up, or showing the way they're split up. But on that first limit, look at the common factor. It's going to be v of x. And then you'll have u of x plus h minus u of x. And that's all over h. Over here, the common factor is going to be u of x. So lim as h goes to 0 of u of x. And you'll have v of x plus h minus v of x all over h. Now I can show these being split into more limits so that we can see them explicitly. But let's try and think about what we've got here. I have 1 over v of x all squared in this first little bit. This v of x is unaffected by the limit, so it just becomes v of x. The rest of what we have here is the definition of u prime. Similarly, over here, this u of x, it just becomes u of x. It's unaffected by h. And this part here, as h goes to 0, is the definition of v prime. And just changing things ever so slightly for alphabetical order, what we end up with is, on top, you'd have u prime of x, v of x, minus u of x, v prime of x, all over v of x, all squared. Okay. Or in other words, without all the x's in, or having the x's implied, rather, u prime v minus u v prime all over v squared. And that does it for the proofs. I'll see you folks tomorrow. But yeah, if the proofs kind of went over your head, don't worry about that. Just make sure you get a little bit of practice in on product and quotient rules. See you later.